So the oceans do many things within the climate system. First of all, they're a great sink of heat. And if you want to warm up planet Earth, then essentially you're mainly warming up the oceans. They're also a place that greenhouse gases that humankind emits to the atmosphere end up. So something like a quarter of all the carbon dioxide that humankind emits as we burn fossil fuels goes into the ocean, is ultimately acidifying the ocean. So that's another sink that the ocean is. About half of the sunlight that enters the climate system from Earth is first entering the oceans and then gets distributed to the atmosphere. The oceans carry heat from the equatorial regions up to the Arctic and the Antarctic. So the oceans also move heat around. The difference that being in the satellite era makes to our observation of the ocean is quite enormous in terms of just the number of measurements that are made. If we look at the historical archives of in situ measurements, we're tending to count data in the tens of millions or hundreds of millions. In the space age, we get billions of measurements. And in a single day, across the suite of sensors that observe the ocean, we see a good fraction of the ocean surface and are able to observe the temperature of the ocean surface from space. So we can blend together the observations of several different sensors, in this case both European and sensors that are flown by the US, synthesize those together to get a global snapshot of the sea surface temperature across the global oceans on any given day. And that's what we have in this animation. So here we have warm waters in red and colder waters of the high latitudes in blue. And as the animation loops through, we're going forward in time at about a rate of a month is taking 1 second. So if we watch the movie, we can see that as the year passes, in this case we're coming into the southern hemisphere summer and the warmer waters are moving more into the southern hemisphere. And then we're coming back into northern hemisphere summer, and you can see the general shift in the warm waters into the summer hemisphere here. There are lots of other details in an animation like this. So for example, you can see the boundary currents on the western side of ocean basins. So the most famous being the Gulf Stream, which is off the coast of North America. So this is a place where the ocean is transporting heat from the tropics to the high latitudes in a very concentrated way. And you can see that warm waters are flowing right up into the North Atlantic and spreading out over the North Atlantic. Other features we can see include the wave motions along the equatorial regions. One of the major phenomena you can see in a movie like this is the El Niño phenomenon. So this is focused in the Pacific, and as you see here, we have these beautiful tropical waves traveling westward across the Pacific Ocean. These are of cooler waters. Periodically, the waters of this part of the equatorial Pacific become much warmer or cooler than average. Just now we are entering, in this animation, a cooler phase. You have the trade winds blowing down here, and then the prevailing winds are blowing across. And they have depressions in them. They blow off Africa with weather systems in them. Some of them become hurricane systems. Data here are from a number of missions. So we have data from the ATSR missions flown by the European Space Agency, blended with instruments called AVHRRs, which are US instruments, meteorological sensors. The way in which we blended them is we take the accuracy really from the European sensors. They're particularly accurate estimates of temperature that we get from those. But we get more coverage by bringing in the American sensors. So we cross-reference those to the European sensors, and this gives a picture of the ocean which is both accurate and, as you can see, incredibly detailed. So we see all this complex activity going on. People often ask me whether these data sets are based on models or simulations. This is just looking at data and seeing activities along the coasts, in the middle of the ocean, sea ice coming and going, the change of the seasons. It's all visible to the eye and very useful in research as well. This is how the satellite data come. This is the observations from one sensor. It's the AATSR, which was a European sensor flown on ENVISAT. Here we have the visible image, and we're flying northwards over the western coast of Africa here, up over Spain, and somewhere under this cloud is the United Kingdom. So this is quite intuitive to look at because it's reflectance imagery, it's visible wavelengths. But that's not what we use to measure temperature, because this strip doesn't tell us about the temperature of Earth. For temperature investigations, we use another wavelength in the infrared, so 11 micrometers in this case. This is infrared data taken at the same time over the same locations. So here is the west coast of Africa again. You can see the land's very hot, it's during the daytime. The clouds come out cold and therefore dark on this image. If you move up here, you can probably just see the United Kingdom. There's Scotland and Northern Ireland. The rest is cloudy. And one key thing you'll notice is that as we go into the night zone, beyond the twilight up here, we can still see the clouds and the sea in between. And that's because we're not looking at reflected light from the sun, we're looking at the emission from the Earth and from the clouds itself. So before we can estimate temperatures of the surface, we need to know where we're looking at the surface and not at clouds. So we create an assessment of where we have a clear sky scene, because we can't see through the clouds at these wavelengths. We mask the brightness temperature, and once we do that, what you can see in this image of the ocean here are subtle variations in the grayscale, and that's telling us that there are subtle variations in the temperature of the ocean in this place. And by combining these observations across a number of different wavelengths, we can correct for the effect of the atmosphere, because we are looking through the atmosphere and that affects the light that we're seeing, the infrared light that we're seeing. But correcting for that, we then retrieve the temperature. And in this strip, this is our final answer, if you like, from this particular orbit. We have the temperature coloured red, again, is warm. As we go up to the waters of the United Kingdom, here's the coast of Scotland again. We've got cold waters off the coast of Scotland and colder waters further north in the Arctic. So we've looked here at one part of one orbit. A sensor like this will do about 14 orbits a day, and we have 3 or 4 sensors available at any given time. And we bring all those together, and that's the data set that makes the animations I showed you earlier, where we have a snapshot of the ocean over the course of a day. One thing that's not so obvious using the colour scale we're using in this animation is all the activity that goes on in the middle and higher latitudes of the ocean. So if we show a movie which has the same data but coloured in a different way so that we can see contrasts in temperature quite easily at all latitudes, we'll see those effects better. So this is an animation of sea surface temperature and sea ice across the global oceans. It's been coloured in such a way that at any given latitude we can see the temperature contrasts in the ocean field. And this really brings out the amazing dynamics and detail that are present in this space view of ocean temperatures. We can see lots of structure. These are eddies all the way across the Southern Ocean. We can see these beautiful tropical instability waves propagating across the equatorial regions. Similarly, we see the strong temperature contrast in the northern hemisphere across the Gulf Stream, and the flow of warm water, this ribbon of water that comes out into the North Atlantic. We have El Niño coming and going, the movements of sea ice, which is another variable involved in the climate change initiative. These all have impacts on our daily lives through the weather. And of course, the aggregate of those changes over the long term is something that we're all deeply concerned about. One of the things we can look for is the constant interplay that happens between the ocean surface and the atmosphere. In the Atlantic, you can see features in the ocean surface that reflect the passage of weather systems and storms across the North Atlantic. When a hurricane passes, it's quite common that there's a wake left in the ocean because the hurricane has mixed up cooler waters from deeper down, and those tracks are reflected in the ocean surface temperature. One of the uses to which sea surface temperature data are put is to look at the health of coral reefs around the world. Corals can die if the waters are too warm near the surface, and from space we can see that directly through data such as these. So something else we can see here is the seasonal sea ice of the Arctic, which obviously extends further south during the course of the winter and then retreats further to the north as summer progresses. Now we're looking here at 2007. This was a year when Arctic sea ice reached a well-known minimum in August, round about now. That's the most northern retreat for sea ice across many of the parts of the Arctic that year. One of the dramatic changes that happens in the ocean from year to year is the El Niño phenomenon. This represents a huge movement of heat from one part of the ocean to the other. So what we're looking at here are 2 consecutive years. We've got 1997 and 1 year later in October 1998. And the red shows an area where the ocean is much warmer than normal, and you can see a complete change in the distribution of this unusual heat from 1 year to the next. And this represents an enormous redistribution of heat across the ocean surface. And also very striking waves propagating across the equatorial Pacific in the La Nina phase. When we have this sort of change in the distribution of the temperature of the oceans, this has global impacts. When the Earth is in this phase, it tends to be warmer on average than in a La Nina phase. We also see shifts in weather patterns all around the globe, most dramatically in North America and Australia and Indonesia. This is an example of why we need to monitor variables such as sea surface temperature, plus all the other essential climate variables that are included in the Climate Change Initiative programme.